Hi, I'm Reed Rector, and throughout the course of this presentation and attached report, Rupal and I are going to be diagnosing the prevention of severe injury accidents. This presentation is going to follow the structure of CRISP DM, and it's going to provide some background information, and then following that, a business understanding, data preparation, modeling, evaluation, and deployment. But first, let's get into our general understanding. In 2021 alone, there were over 6 million police reported crashes in the United States of America. From that, almost 2.5 million people were injured and 42,000 lives were lost. This is not something that is decreasing. In fact, over the course of the past 10 years, from 2012 to 2021, there has been a 27% increase in fatal accidents. This is a major issue, and this is something that needs to be addressed. As of right now, this is the leading cause of death for people under 40, according to CDC. But this doesn't just affect young people. Statistics say that over 77% of people are likely to be involved in a car accident during their lives, and the average person is involved in 3 to 4 car accidents throughout their time. So what can we do to turn the tides of this tragedy through technological innovations? What can we do to ensure that we can use a high-tech, low-code solution to save lives and, under the spirit of Siemens, work to create a better tomorrow with us? Now, let's get into first the data that we're going to be using for this report. We're going to be using the NHTSA crash report sampling from 2021. And through the data we're accessing, we are viewing 4 of the 28 files that are used in that report. But within those files, we're going to be talking about the person file, the vehicles file, the accidents file, and the distractions file. And all of these combine to create a narrative of everything going on through the accidents of this year. Our total set of files have over 128,000 records, featuring 95,000 motor vehicles throughout all of these reports, over 54,000 reported crashes, and in our distraction file, we see 20 different types of distractions. Now, I'm going to pass it on to Rupam to talk a little bit about data preparation for this project.
Thank you, Reid. So before developing the model, we need to improve the homogeneity of the data so that the model can focus on trends rather than the noise. To achieve this, several cleaning steps were followed. From the variable injury severity, we removed any values with uncertain or unknown severity. From deformation, we only included data that indicated some level of damage to the vehicles. We also wanted to keep our analysis limited to automobiles only. Therefore, other type of vehicles like motorbikes or trucks were excluded. The predictive model we would like to develop will only focus on the injuries sustained by the occupants of the motor vehicles. Therefore, pedestrians and other types of individuals were excluded from our analysis. So most of the categorical variables we had in our data had high cardinality, which, if not treated, may make the learning algorithms overfit the rare categories. Feature engineering was mainly done to reduce those cardinality and also to create some new features. In 9, these steps were completed utilizing the rule engine and the math formula nodes. We used both feature and response binning to understand that we are able to reduce cardinality and place the different levels of injury severity into 2 categories, low and high, so that this problem can be considered as a binary classification problem. In addition to the existing variable, we also created a new variable called vehicle age by subtracting the current year 2021 from the model year of the vehicles. The original dataset had more than 100 variables. All of them, of course, are not necessary to classify injury severity, and having them might increase the computational time. Therefore, we had to reduce the number of variables. 2-step feature selection process was employed to identify input variables that are absolutely necessary in predicting injury severity. At first, 38 variables were selected based on previous studies, common sense, and statistical analysis. The variables that had extreme association with injury severity were excluded. Then backward feature elimination node in 9 was utilized to select the final set of 30 input features that are absolutely necessary to improve the predictive performance of the models. So after making all these changes, we are able to trim the dataset from over 128,000 records to 57,000 and trim from over 100 variables to just 31 variables, including the target variable injury severity. So now that we have the data prepared, we can start building models to classify the injury severity from car crashes. But before developing the models, we need to split the data into training and validation set. In this study, instead of having a single split of train and validation data, we used 10-fold cross validation. We also had significantly higher records of low injury than high severity injuries. So to balance this class distribution, we used equal size sampling technique in 9. The next step was to select the algorithms to develop the predictive models. We selected 7 different binary classification algorithms to develop the models. So this is the complete workflow of model development and evaluation. I'll briefly talk about each of these models in my following slides. So the decision tree was our first model, and it works by creating a set of if-else rules to classify the data. The figure on the right side shows the first 2 levels of the tree trained on the car crash data. High injury severity is colored as red and low as green to understand the tree better. As can be seen, decision tree identifies airbag deployment as the most important variable in classifying the injury severity. In cases of when airbag is deployed, majority of the injuries are classified as high severity. This correlates with the nature of the accidents. In cases of minor crashes with low severity, the airbag might not even deploy. Hence, the airbag deployment is correlated more with the high severity injury classes. The next model that we use is random forest one, is the forest of decision trees. Instead of using one single tree to make the decision, random forest combines the results from several uncorrelated decision trees to make the judgment. In this work, the default setting of RF in 9 is used to develop the random forest model. Then we have extreme gradient boosting, which is another tree-based ensemble model, but it is different from random forest in the way each models are built. Each models are built sequentially on the error made by the previous models. Hence, they can correct the errors made by the weak learners and make the better predictions. We experimented with different configuration of XGBoost, and the figure on the right side shows the configuration produced the best result for us. Then we used FNN, a simple type of artificial neural networks. In FNN, information are passed on forward direction from input layer to the output layer through some hidden layers, and then they're adjusted with weights and bias. In this study, we used 2 hidden layers with 10 neurons per layer to architect the FNN model. Because FNN is a number-loving algorithm, categorical variables are hot encoded and numeric variables are normalized to have a mean of 0 and standard deviation of 1. We also use naive Bayes, which is the most simplistic type of statistical algorithm that applies Bayes' theorem to classify tasks based on the probability density function of the input data. Similar to FNN, here also the numeric variables are normalized to have a mean of 0 and standard deviation of 1. All right. Then we had the SBM. SBM is a support vector machine algorithm which works in such a way that it finds a hyperplane that can separate 2 classes of data with the highest sense of purity. SBM also lets you select different kernel functions that are required to transform your input data into a higher dimension. In this study, we used RBF as the kernel function. RBF, or the radial basis function, is the most commonly used kernel for capturing complex and non-linear relationship. The final model that we had in our arsenal is the logistic regression. This is the most popular statistical based learning algorithm, and this is our favorite one. This works in a very similar fashion how linear regression works. It tries to fit a line to predict the log odds of probability of getting a yes response. In our case, the probability of getting high injury classes. All right, so this is how these models actually performed during cross-validation. This is showing you the accuracy. So when we initially completed our analysis, we had a very high accuracy values. This is probably higher than most of the previous studies that have been done, to predict the injury severity. After digging deeper, we realized that the variable for hospitalization was artificially inflating the accuracy values because of its strong association with injury severity. Almost all the individuals who were sent to hospital, they also had high severe injury. Therefore, we removed this variable from the feature list and reevaluated the accuracy of the models. So this shows you the revised accuracy when hospital is not one of the input features. Though we found a decrease in the accuracy after removing the variable hospital, this actually gives more better representation of the model performance. We might have a lower accuracy than most of the other groups who have done this work, but this actually shows the true representation of the model performance. From this, we can see that naive Bayes was the most accurate model, followed by random forest and logistic regression. We also found that SBM with RBF is not performing really well. This is probably due to the class imbalance technique we used. However, accuracy is not everything, especially when we are dealing with imbalanced data. We need to see the sensitivity and the specificity of the model to evaluate those models well. Therefore, we actually compared the ROC-AUC score of the models. ROC-AUC combines the specificity and the sensitivity of the models, to show you how good the models is in classifying those two different types of injury severity. Based on this, we found that logistic regression is our best classifier, very closely followed by random forest in terms of ROC-AUC score. Once more, though these values are likely smaller than other groups, we believe that they are a more accurate representation of the model performance. All right, the goal of this study was not just to predict the injury severity. We also wanted to see like how different factors are associated with injury severity. Like that, we wanted to do the sensitivity analysis. So following the evaluation of our models, we performed a sensitivity analysis to rank risk factors based on their importance in predicting injury severity. The variable on its removal dropped the accuracy most, has more sensitivity to the model. Then those sensitivity scores from each models were normalized with the predictive power of the model. The model that had highest ROC-AUC score was given more weight. Finally, those weighted sensitivity scores of each variables from every models were combined and normalized again to have importance score in the range of 0 to 100. I will now pass it over to Reid to talk more about the sensitivity analysis and talk about how different risk factors are associated with injury severity. Over to you, Reid.
Thank you very much, Rupam. Now let's tackle the results of the sensitivity analysis. As seen in this graph, you can see all of our different factors grouped in factors of importance based on high risk, seen in red, moderate risk, seen in orange, and low risk, seen in green. And here are the high risk variables in terms of order. The most high risk variable and the most important variable is the use of a seatbelt or a restraint. Followed by that is the presence of an ejection in the crash at 91% importance. Next is whether or not an airbag went off at 88% importance. On fourth place is the presence of a rollover or an overturn in the crash at 65% importance. And in fifth place, with 60% importance, is the location of a rollover if it's present. Now, we have all this great data, but what can we do to ensure that we are making good happen through all this work? Well, I think Siemens has the perfect opportunity to address this problem while also meeting a current national initiative and strategy. In 2022, the National Roadway Safety Strategy was created to focus on saving lives on every single road in the nation. And one of the major focuses is coordinating post-crash care. A crazy statistic that I read is that 40% of traffic deaths, the patient is alive whenever the first responders arrive. And I think that's a perfect place for Siemens to address and develop a solution. And from that, we developed the Siemens Accident Injury Initiative. So, one of the big initiatives that the nation is putting together is the initiative of next generation traffic incident management, which essentially puts together all the data and communicates seamlessly between the traffic site to every single relevant partner. And there are federal grants in place for states to initiate through the Prevent Roadside Deaths grant. I think Siemens has the perfect opportunity to create specialized accident care plans to ensure that you are using the Siemens Health and Years tools and plans to ensure that every single potential high frequency accident already has a plan in place, already has a tool in place, and can be saved through the Siemens tools. And I believe that through this, we can shape innovative solutions to statistically likely emergencies. Now, what does that look like? How does that happen? This needs to be done through the creation and utilization of important value partnerships. I think Siemens should partner with EMS and hospitals all throughout the country to create communication and utilization plans to ensure that all of the work done to save lives is done through Siemens. And I think it can start with already existing value partnerships like WakeMed and the Medical University of South Carolina. Now, let's wrap everything up with a conclusion. The most important area of concern and the most important takeaways are that seatbelts save lives and prevent infections, and rollovers bring great risk to passengers. Through our sevenfold analysis, even though we might have had a decreased qualitative accuracy, we found an increased relevant accuracy, and we were able to find all of the most important values. And we believe that through the Siemens Accident Injury Initiative, we can work to save lives and provide solutions for this large global need. So, with this, thank you very much for your time, and let's work to save lives and create a better tomorrow with us. Thank you very much.